Welcome to the Silicon Language Foundry. Traditional AI infrastructure is bottlenecked by layers of OS abstraction. Our philosophy bridges that gap, compiling high-level, safe semantics directly into hardware state, what we call the monad-on-chip architecture. Watch as we lower the representation straight to the bare metal data plane. We are about to run the full three-stage deterministic benchmark on this ARM Neoverse instance. Stage 1 measures the Linux kernel's native XFS storage path using vIO. Stage 2 benchmarks our Fuse user space bridge. Stage 3 unleashes SPDK dev perf for full kernel bypass. Each stage runs at Q depth 1 and Q depth 16, the knee of the CPU saturation curve. Let's go. Azure Host Preflight is active. We are sanitizing the target device and resetting the execution environment. Stage 1 is live. This is the kernel baseline using vIO through the native file system path. Stage 2 is live. The user space Fuse bridge is now under load, preserving control while exposing the kernel tax. Stage 3 is live. We are now measuring the bypass path, pushing directly toward SPDK on bare metal queues. Those numbers are live, measured right here on real silicon. At Q depth 1, SPDK delivers sub-25 microsecond latency, more than 2x faster than the kernel path. The kernel tax includes XFS metadata lookup, the block layer scheduler, and the interrupt-driven completion path. Our lock-free submission and completion queues bypass all of it. Bridging hyperscale infrastructure and bare metal performance requires global vision. Ping is exploring engineering leadership opportunities. He leads teams and AI agents building systems that bypass the kernel, not the details. Let's scale the next-gen AI data plane together. Now transitioning to AWS Graviton3 for cross-cloud validation. The same zero-copy data plane architecture will demonstrate hardware portability across Neoverse implementations. Launching kernel baseline benchmark on AWS Graviton3. We'll measure stage 1 kernel vIO performance at Q depths 1 and 16 to establish the baseline throughput. Stage 0 is sanitizing the target device and resetting the execution environment for a clean benchmark baseline. Stage 1 is now running kernel vIO benchmarks. This measures Linux XFS performance through the standard file system stack. The kernel baseline establishes our performance foundation. Each I/O operation travels through VFS, block layer, and hardware queues. Now transitioning to Stage 2, User Space Bridge Demonstration using Fuse. This bypasses the kernel VFS layer while maintaining file system compatibility. Stage 3 begins, SPDK Preflight Verification. The system is rebinding the NVMe device from kernel driver to user space vFIO for direct PCIe access. SPDK DevPerf now has direct hardware control, running latency and throughput benchmarks with zero kernel overhead. AWS Graviton3 kernel baseline complete. Now parsing the performance results. The scorecard confirms consistent kernel performance across cloud platforms. This validates our hardware portable architecture foundation.